Thank you, Julien. So I'm Cédric Chevalier. I will present Triclade and what we have done with CExA. So I am not directly involved in Triclade. I am on the CExA side, and I do the presentation on behalf of France volunteers that cannot do it today. So some context, so Triclade is a code to simulate turbulent binary missing in a highly compressible environment. It relies on Navier-Stockes equation. It's used structured Cartesian mesh, and it has shock capturing numerical schemes. So I will not be able to describe in depth all the physics. Yeah, for me, it do nice picture like this kind of mushrooms, but we will focus more on the computer science part. So it's a legacy code. It has almost 30 years old. It's 100,000 lines of C++, but mostly C. It's C++ that look like C. So even the file were named C. But it has some designs that come from C++ and object-oriented programming. So it is designed to be modular. So one numerical scheme is coded as one module. And it has few external dependencies, so MPI to do distributed computing, FFTW to do some kind of post-processing. But it has quite a lot of internal libraries. So the design was clever and modular, but they have in-house I/O, initialization, post-treatment, and all of this with a proprietary data format. So it's quite a lot of code if you look at the whole picture. And a lot of tooling in form of Python scripts around the code. So the first development, it was to modernize the workflow. So we have put the source code on one of the GitLab hosted at CA on Inti, on the DAM side. We have updated the user and the developer documentation. And one of the first contribution we have made is to upgrade the build system to go from a kind of non-standard makefile to CMake, as it's more robust to navigate in the code when you don't know the application. And we have developed and set up a testing suite, and we back up all reference results. So the goal for CExA is to help to port only a part of Triclade. So at the time, we thought that it was only 10,000 lines of code to the part to be port, but we will see that there is some hidden links between all the code, and it might be a larger effort to port only this few numerical schemes. So the idea to migrate to Kokkos was to replace the code variable, so it's custom data structure, with Kokkos view. So Kokkos view is the main the data structure of Kokkos. But in fact, we have several types of variable. We have the primitive types, their lifetime span across the whole execution. And we have some conservative variables where their lifetime is only a method or a class instance. So we have to manage them perhaps differently. And we have some sort of generic management for this kind of variable using projects that are around CExA like DBC. And perhaps we will need some collection of variables. So it's things that are think about and design in CExA for a Triclade, but also for other applications. So the second step will be to rewrite computing loops. So currently we are not sure that all the code path is thread safe. So we have to characterize it. And if it's not, it will mean that we need a deeper refactoring of the code. And after, when it's thread safe, we can go for a parallel for plus a lambda, like we write code in Kokkos. And we already have some thought to exploit hierarchical parallelisms. We can use different teams along the geometrical axis to improve the parallelism. So the current state is, this year was mostly about the design and the implementation of a test framework to help assessing the code validity. We have introduced a new dependency that is level DB. It's a small database to store the results and to be able to compare efficiently the results. So it's hash table like database. And we have comparison tools. So what we learn also discussing with people from CExA is it's better to have no abstraction over Kokkos or very small abstraction. So we will try to use directly Kokkos views on parallel form. And we had done some change in each part of the code to add new option to the user to be able to choose a new implementation. And we had been pushed the Kokkos view initialization. So we encountered some technical issues. So the main one, I will say, is as we want to modernize all code database, we want to be able to handle at the same time both the legacy part and the Kokkos part. And the legacy part was not really well structured, I will say. Most of the data type are in the form of plain old data and pointers, and the pointers of different levels. And it's explicitly passed as parameters for all function and methods. So it's quite complicated to modernize this part. And the memory allocation are scattered in some function that are called everywhere, from the main for the primitive type, but also from inside objects and function. And one other thing that have been complex to deal with is all the modules implement some interface. So when we want to create a new Kokkos module, it's as all the call of the module are going through the interface, we have to match the current interface, and it does not use Kokkos data type. So it ends up with it's considerably more refactoring than expected. It's not just going parallel and going GPU. We have to set up the code in a better shape. And so we have several strategies to do it. We can fork the code and delete all the paths we will not take and have a Kokkos only part of Triclade. We can do massive string replacement and pray, or we can have a small abstraction mechanisms and update the interface. So it's the way we have selected, and part of these abstraction mechanisms has been presented by Paul and is available in the BRAC project. So, as a small conclusion of 1 year of development, so the GPU part of Triclade has really begun now, in fact, with some delays due to the refactoring pre-migration I have described. And the goal is still to have a first run on Grasshopper, so on CExA 1 HE by the end of the year, with some kernels on GPU. The preliminary overview has underestimated some difficulties that are interdependent. So it's easier to analyze after than before. So the lack of common abstraction data type, this nested row pointers, is really hard to modernize. And so I explained that quite a bit. The lack of a proper testing framework was also annoying. So Kokkos has migrated from some internal network to other computer, and we cannot rely on all the stuff that the Triclade developer were used to. And one thing also, it's when you take, I will say, all legacy code, you have some technical debt. And for example, to go to Kokkos, we have to use modern C++ and modern C++ compiler. It ends up to have a lot more warnings that we are used to. So when you try to correct the warning, you find bugs, memory leak, and the code was not multi-threaded, so we don't have any guarantee about the thread safeness. So these difficulties are not linked to Kokkos. It's the way it is to adapt an existing code to GPU. So it's one of the drawbacks to do this incremental move to GPU. Writing a new code can go a little bit faster on this point. But being close to CExA helps us to for the design and the technical choice, and is the development of some helper tools like BRAC, and some of the ongoing works like Kokkos.com or Kokkos FFT are also of interest, and will help us to go faster next year.
Thank you very much.